Everyone, today's lesson is going to deal with strong versus weak acids and how that's different than concentrated versus dilute. So oftentimes we use the term strong and concentrated as synonyms, although they do not mean the same thing at all. So we'll get started right away. We'll pull up the PowerPoint, and here we go. So we're going to deal with concentration versus strength. That is the difference of an acid can be concentrated or dilute. That has to do with how much water is added to it or not added. Whereas strong versus weak has to do with how much the acid dissociates and has nothing to do with its concentration. We'll find out that you can have a dilute acid that is strong, or you could have a dilute acid that is weak. You could just as easily have a concentrated acid that is a weak acid, or a concentrated acid that is strong. All of these are possibilities. Now, what is all this laughing about? Let's see if we can figure it out. More laughing. Okay, I think they're done. So I've got a grid here with 4 different quadrants. Now, for the top 2 grids that I'm going across here, these both represent strong acids. So we've discussed monoprotic and diprotic and polyprotic and how those dissociate. So what you want to notice is all strong acids dissociate nearly 100%. So we have my acid, my HA, a single arrow indicating that it all breaks down into H plus and A minus. So when I look at my dilute, I see very few ha-has here. Almost all of the acid has been dissociated into the protons H plus, A minus, H plus, A minus. On the left side, all of these are basically broken down. There's very few ha-ha-has. They're almost all dissociated. So these are all strong because they've dissociated fully. Over here on the left, I have many more species present, so therefore it's concentrated relative to the right. It's more dilute. Now on the bottom 2 quadrants, I'm representing what I'm going to call weak acids. And it says here weak acids dissociate very little. So we have the HA, our acid. It does donate a proton and an anion, but notice we're representing this with double arrows, and the arrow tends to point back toward the reactant, indicating that the majority of the time it wants to stay as HA, not H plus and A minus. So on the weak concentrated acid, I see I have a whole bunch of whole bunch of acid that hasn't dissociated. There's a small amount, maybe 20%, that has dissociated. But most of it is all together. And then on the weak dilute acid, I again have most of the molecules staying together, very few breaking apart. So weak has to do with how much it dissociates. If it dissociates very little, it's a weak acid. If it dissociates fully, it's a strong acid. Concentration, on the other hand, has to do with how many things I have present. If I have a lot of things present, it's concentrated. If I have less of them, it is dilute. I hope this makes a little bit more sense what the words strong and weak, concentrated, dilute actually mean. So we could put this in a data table. A strong acid, if we look at it, is not reversible. That means it's a one-way arrow going from reactants to products. The Ka, this is a new term for you. This refers to the acid dissociation constant. And the larger the numerical value for the Ka, the stronger the acid. For a weak acid, it will be reversible, which means there'll be two-way arrows. So what would you expect for a Ka value of a weak acid as compared to a strong? If you said a smaller value, you are correct. So what do I have represented here? I've got an acid and water, Is this a strong or weak acid? What do you think? Can't tell? Look more carefully. Look right in this middle region, right in here. What's that trying to tell you? Good. That's a weak acid. Notice that the arrows don't have to be one larger than the other, but as long as you have a double set of arrows, that's going to represent a weak acid. The equilibrium expression for any equilibrium is going to be the concentration of products divided by reactants, although we won't need to add in water. So Ka is equal to the concentration of the product, H3O plus, times the concentration of A minus, divided by the concentration of the initial HA. Now let's think about this for just a moment. If the majority or all of this were to break down and turn into the ions, we'd have a very large number on the top divided by a very small number left over. A big number divided by a small number is still a big number. So that what that says is, if it breaks down fully, like a strong acid, the Ka will be a large value. So Ka are big numbers, strong acids. And what that means is we're going to get basically only the H plus and A minus left over. There'll be very, very little HA present because it's all broken down for a strong acid. Lots of product, very, very little of the reactant for a strong acid. Notice I've substituted, instead of writing the hydronium ion H3O plus, recall hydronium and hydrogen ion are the same thing in water. So I'm only putting H plus up here, although I could have put in H3O plus. Now, for a weak acid, if we go back to this equation, a weak acid, most of it is going to stay together. Very little is going to dissociate, which would mean you have a small number on top divided by a big number. A small number divided by a big number is a really small number. So weak acids will have very small Ka values. Small is a number like 1.8 times 10 to the negative fifth. That's the Ka value for acetic acid, a weak acid. And finally, what's going to be present is we'll have a little bit of everything. We'll have some H plus, we'll have some A minus, and we'll have quite a bit of HA, but all the ions will be present in a weak acid. Trying to show you this visually here, strong versus weak again. We're not discussing concentration. Remember, that's different. This has to do strong and weak with how much it dissociates. A strong acid, before dissociation, has only the acid there. After dissociation, it has only ions present and no HA left. It's all dissociated. Okay, so we can see those ions floating around. And because there's so many ions floating around, strong acids are also strong electrolytes. Let's compare that to the bottom where we have a weak acid. So on our weak acid, we have a certain concentration we begin with, and after we put it in water, it dissociates. We have very little H plus and B minus. The majority of it stays as a weak acid, so very little of it, maybe 20% or less, dissociate. So when we look inside the beaker, there's a few ions floating around by themselves here and here, but most of them stay together as an acid. Because it has so few ions in solution, it gives up very little H plus. It is a weak electrolyte. So let's review concentrated and dilute one more time. If I said something's 0.3 molar HCl, I could argue that is a dilute strong acid. Now, the dilute is relative. HCl is always a strong acid. There are 7 strong acids. Your teacher might make you memorize them. I will not make you memorize the 7 strong acids in your first year chem class. If you take AP Chem, that will be something I will expect you to know. Now, why did I call 0.3 molar dilute? Well, if I compare it to a solution like 2 molar, 0.3 is a dilute strong acid relative to a 2 molar HCl concentration. If, though, I were to compare 2 molar, well, let's say this another way. 2 molar HCl as compared to 0.3 would be considered concentrated relative to the 0.3, but still a strong acid. Or relative to 12 molar HCl, 2 molar HCl would be considered dilute relative to 12 molar. Again, concentration is always relative. In each case, HCl is a strong acid. Now, if I took 10 molar, do you recognize this acid? That's right, that's acetic acid. Acetic acid is always a weak acid. Now, 10 molar is probably a very concentrated concentration. What would be more dilute than 10 molar? Well, 1 molar, 2 molar, 3 molar, 5 molar, 7.8 molar would all be dilute in comparison to 10 molar. All right, I told you this is going to be a shorter lesson, and I hope you understand the difference between concentrated and dilute. If an acid is strong or weak, has to do with the acid itself. It has nothing to do with concentration, and we cannot change it. Concentration is relative, and we'll say it's either dilute or concentrated by comparing it to something else.